2, exponential functions. We've evaluated functions in which the variable is the base and the exponent is any real number. For example, y equals x to the fifth has x to the base and 5 as the power. This is known as a power function. Functions of the form y equals b to the x, in which the base b is a positive real number and the exponent is a variable, are known as exponential functions. Consider the graph of y equals 2 to the x, where x is an integer. This is a function since there's a unique y value for each x value. And so we can plug in a bunch of x values and evaluate the y value 2 to the x for those values of x, and if you plot them on a graph, it looks like this. Suppose we expand the domain of y equals 2 to the x to include all rational numbers. These additional points are going to fill in the graph of y equals 2 to the x, and so we get a smooth curve. The graph y equals b to the x has different characteristics depending on whether your base is greater than 1 or between 0 and 1. Although mostly they are very similar. They both have the domain of all real numbers. Your range is all positive numbers, so I would probably write this as from 0 to infinity as your range. An intercept at y-intercept at 1, no x-intercept because 0 is not in the range. Continuous 1-to-1, it is increasing on the b greater than 1 and decreasing for the b between 0 and 1. Horizontal asymptote along the x-axis in the negative direction for the b greater than 1 and in the positive direction for the b between 0 and 1. No vertical asymptotes. Like all functions, exponential functions obey transformation rules. So if this is our 4 to the x function, if we add 2, we shift the whole function up by 2. We subtract 3, we shift the function down by 3. If we make it negative, put a negative out front, we're going to flip it over the x-axis. If we multiply it by 6, that's going to end up compressing it in the horizontal direction, and so on and so on. According to Newton's law of cooling, the difference between the temperature of an object and its surroundings decreases in time exponentially. Suppose a certain cup of coffee is 95 degrees Celsius and it is in a room that is 20 degrees Celsius. The cooling for this particular cup can be modeled by the equation y equals 75 times 0.875 to the t, where y is the temperature difference and t is time in minutes. Find the temperature of the coffee after 15 minutes. So plug in 15 for t, so 75 times 0.875 to the 15, and we're going to have to do that on our calculator. And that ends up being 10.12. Right? Y is the temperature difference. So the difference between the temperature of the cup of coffee and 20 degrees. So we'll call it C for coffee. Minus 20 degrees is equal to 10.12. Add 20 to both sides, and so our cup of coffee is now 30.12 degrees Celsius. In a situation like cooling, where a quantity loses value exponentially over time, the value exhibits what's called exponential decay. When a quantity increases exponentially over time, that is called exponential growth. Can you think of some things that exhibit exponential growth? Populations often exhibit exponential growth. Bacteria in a petri dish. Compound interest is an example of exponential growth. Very important equation. The equation n equals n sub 0 times 1 plus r to the t, where n is the final amount, and 0 is the initial amount, r is the rate of growth or decay per time period, and t is the number of time periods, is used for modeling exponential growth or decay. R is positive for growth and negative for decay. In recent years, beekeepers have experienced a serious decline in the honeybee population in the United States. One of the causes for the decline is the arrival of varroa mites. Experts estimate that as much as 90% of the wild bee colonies have been wiped out. Suppose that a researcher estimates that the initial population of varroa in a colony is 500. They are increasing at a rate of 14% per week. What is the expected population in 22 weeks? Right? So, this is so we're using the n equals n0, 1 plus r to the t. So, the initial population of varroa in a colony is 500. That's our n0. N0 is the initial amount, which is 500. They are growing at a rate of 14% per week. So we're going to write that as a decimal, 0.14. It's growth, so it's positive. And our time t is going to be 22. So we're going to get 500 times 1.14 to the 22. And that ends up being 8,931. A variation on our exponential growth formula is used to find compound interest. Compound interest is when you invest money. When the interest is compounded, the interest that you earn on your money goes into the account and you start earning interest on your interest. And that's what makes compound interest an exponential function rather than a linear function. If you earned 5% on your money per year, but it didn't compound, you would earn the same amount per year and your money would grow linearly. With compound interest, if you earn 5% per year, when that money is compounded, it goes into the account. And so you earn 5% not just on the original amount, but also 5% of that 5% interest. And that's what makes the money grow exponentially. So the compound interest formula, very similar to the exponential growth formula. A equals P times 1 over Rn to the Nt. P is the principal, that's the amount that you start with. A is the final amount, R is the interest rate, N is the number of times the interest is paid or compounded. So if your interest is compounded yearly, your N is 1. If your interest is compounded semi-annually, your N is 2. If it's quarterly, your N is 4, and so on. And T is the number of years. So the amount of money in a money market account providing an annual rate of 5% compounded daily if Marcus invested $2,000 and left it in the account for 7 years. So P times 1 plus R over N to the NT. Our principal is $2,000. Our interest rate is 5%. And we are compounding this daily, so our N is 365. 365 times compounded per year. And then for 7 years. So if we plug all of this into the calculator, 2,000 times 1 plus 0.05 over 365 and raise that to the 365 times 7. And he's going to end up with $2,838.07. For money, we want to round to the nearest penny. For populations, round to the nearest individual. And that's it for exponential functions. Tune in next time to talk about my favorite number, the number e.